We're going to continue our introduction to light by asking the question, what is light? Light is an electromagnetic wave. And what that means is that light is actually a combination of both electric and magnetic fields. An electromagnetic wave is capable of moving through a vacuum. Electromagnetic waves do not require a medium to travel through. So that's how light from the sun gets to the earth, traveling completely through empty space, so that there is no medium. The other waves we've been studying, slinky waves and sound waves and waves in the ripple tank, are examples of what are called mechanical waves. Mechanical waves cannot go through a vacuum. They cannot send energy through a vacuum. They require a medium to get their energy from one location to another. So the slinky waves require a slinky. Sound waves require air. Waves in the ripple tank require water. Can't have sound waves without there being air. Can't have slinky waves without there being a slinky. So what does it mean to say light is an electromagnetic wave? What does it mean to say that an electromagnetic wave is a combination of electric and magnetic fields? So to explore this, let's watch this simulation where you're going to have this green dot here move up and down. That's a charged particle, and it's going to vibrate this way. And as it vibrates up and down, it gives off these waves, which are electromagnetic waves. Now, what's electromagnetic about them is the red lines represent electric fields. The long lines mean strong electric field, the shorter lines are weaker, and these ones are pointed upwards and these ones are pointed downwards. The blue lines represent magnetic field, which is vibrating this way. So the electric field is vibrating that way, magnetic field is vibrating perpendicular to it. And magnetic field too has strong values and weak values, and some point this way and some point that way. And they constantly are streaming off of this charged particle. So we would say that these are electromagnetic waves. This is exactly what light is like. So why is this happening? Well, we've seen two things in the course so far that would show us how this works. And one is when we use Castle, we put a compass under a wire, and when we connected the circuit and the light bulb lit, the compass needle moved. And what that told us is that when you have an electric field, which is what was causing the current in the wire, it makes a magnetic field, which is what made the compass move. So electric fields that are changing make magnetic fields. Likewise, if you remember when we studied electromagnetic induction and we waved magnets near loops of wire, waving magnets near loops of wire made current. And what that taught us is that changing magnetic fields also make electric fields. So changing electric fields make magnetic fields, changing magnetic fields make electric fields. And that is exactly what we're seeing here. As the charged particle vibrates up and down, it makes an electric field which is changing. That changing electric field makes magnetic field. But the magnetic field is changing, and the changing magnetic field makes electric field. So what you have is changing electric field making magnetic field, changing magnetic field making electric field, and that is what an electromagnetic wave is. It literally generates itself, and that's why it needs no medium, and that's why it can travel through a vacuum. Wow, that seemed pretty complicated, didn't it? Well, we were talking about light, and now here we are talking about electric fields and magnetic fields. Well, if we figured out how fast electric fields can make magnetic fields and how fast magnetic fields can make electric fields, we would see a really interesting thing. The speed that that process happens at is 3.0 times 10 to the 8th meters per second. That's how rapidly electric fields make magnetic fields make electric fields, and you might recognize this as, that's the speed of light. So that is the speed that electromagnetic waves travel. Now, if like any other wave, electromagnetic waves can have all different frequencies, and they can have all different wavelengths. And so this chart, which is on your reference tables, is kind of putting all together in one place all of the different names of different frequencies and wavelengths of electromagnetic waves. So we call the whole thing the electromagnetic spectrum. The key element to realize, actually two key elements to realize here, is all of these names, some of them are familiar: radio waves, microwaves, X-rays, ultraviolet, visible light. It's all the same stuff. The only thing that differentiates these different types of electromagnetic wave is their frequency or wavelength. They are fundamentally the same stuff. So down here at very low frequencies and very long wavelengths, you have radio waves. A little higher frequency, you have microwaves. It's a little higher frequency. Higher frequency than that, you have infrared, which you and I would call heat. Higher frequency and shorter wavelength than even infrared is visible light. And notice all the colors are listed here, and the colors all together are crammed into this tiny slice of the electromagnetic spectrum. And that means of all of these kind of waves, the only ones that we can see is this tiny band here, which in this diagram is exploded out to show all the colors. So red has the lowest frequency of any of the colors, violet has the highest, and red has the longest wavelength, violet has the shortest. And then you have ultraviolet, which causes sunburns, and then you have X-rays, and then you have the highest frequency and shortest wavelengths is gamma rays. So these are all fundamentally the same thing, and it is very important to remember that everything on this chart travels at the speed of light. So when we had learned the formula V equals frequency times wavelength for waves, the V was the speed of the wave. But now we write the speed of the wave is the speed of light equals frequency times wavelength. So every one of these waves travels at that speed. So whereas before this number could be different, now this number is a constant in a vacuum. The speed of light in a vacuum is a constant number. So these numbers down here, the frequencies, and these numbers up here, the wavelengths, are related by this formula. In fact, if we only knew this frequency and we knew the speed of light in a vacuum, we could calculate the wavelength. So this is called the electromagnetic spectrum. You are looking at the Milky Way. Picture that's taken, as any pictures we would take are, in visible light. You're looking towards the center of the galaxy, but as we've now just learned about the electromagnetic spectrum, visible light is a tiny slice of the electromagnetic spectrum. So actually, we are looking at the center of the Milky Way with only a very narrow range of frequencies. So let's see actually what the Milky Way would look like at different wavelengths. Here's the same part of the sky, the same Milky Way picture, but now we're looking with a hydrogen alpha filter. So we're looking only at wavelengths at the very red end of the spectrum. And notice that I'm already seeing some features here that are different than in visible light. So we're seeing that the Milky Way is emitting radiation at frequencies and wavelengths other than just visible light. This is the same picture again, but now it's taken looking only at near infrared frequencies or wavelengths, and that's in the infrared band, but it is close, the near means close to visible. And I'm already noticing that there's structures like here that if I look on the visible picture just seem to be stars, but if I look at a different wavelength, all of a sudden the structure is a lot more pronounced here, showing that some objects in space actually give off very little energy in the visible, and they give off lots more energy in other bands of the electromagnetic spectrum. Here's the same picture in far infrared. This is wavelengths that are much longer than red or visible light wavelengths are. So this is the far infrared part of the spectrum, and notice you can see features that are different than at visible light. Here we are at even longer wavelengths, even lower frequencies. These are microwave frequencies. So you notice that this picture, this is the Milky Way still, we are seeing a very different picture than we would see in visible light. The universe is broadcasting information in all the wavelengths of the electromagnetic spectrum, not just visible light. If we look at the microwave sky, we can see that there are features here that are not on visible light. Now here we're looking at radio waves, which have the longest wavelength and the lowest frequency in the electromagnetic spectrum. And I'm noticing a structure like this right here. If I go back to the visible picture, I'll just see a little point of light, a star there. But this star is a major emitter of radio waves, which I would not notice how prominent it is in radio waves if I just looked at the visible light spectrum. Lots more energy at very low frequencies. Now we go way above the frequencies of visible light. So we are in the X-ray part of the electromagnetic spectrum, and we are seeing features that you don't see in visible light. Very, very different part of the sky. But again, the sky is broadcasting in all different wavelengths of the electromagnetic spectrum. And finally here we have the highest frequencies in the electromagnetic spectrum, gamma rays. So here again we have maybe little sources of gamma rays here that if we looked at the visible light picture, you wouldn't even see any of this stuff because they primarily broadcast in gamma ray frequencies. So the universe is not worried about the fact that we only see visible light. The universe is broadcasting in every band of the electromagnetic spectrum.